Welcome to Lesson 2, Example 4, and it asks to compute the reactions and draw the shear diagram for the beam shown below, neglecting the weight of the beam as usual. And this is 15 foot. And we're going to go ahead and start. If you remember, three equilibrium equations are as such. Let's go ahead and write them down. And they are horribly important. Sum of the forces in the x direction equals 0. Sum of the forces in the y direction equals 0. And the sum of the moments about any point will equal 0. And there aren't any in the x direction, and there's 2 in the y, so we have to go ahead and eliminate one of these so we can figure out the other one. And by doing that, we eliminate one by saying that times 0 is 0. The force times the distance is a moment. So the force, which is R2, times the distance, which is 0, is 0. So we're going to go ahead and call this A. Point A. Let's go back a little bit. Let's do this in color. Alright, we're going to call this point A and point B, just to make things a little bit more clear. We will go ahead and sum it about point A. So we're going to say this is the positive direction, and the sum of the moments about point A equals 0. R1 times 0 equals 0. And that's how we isolate R2. And we're going to have a positive. I'm going to try to go a little bit faster since I think you're there. And I believe we've already done this example, but we're going to do it again because it's very important to have a firmly grasp this understanding. And it says to do the shear diagram. We're going to do the moment as well, just for more practice. And we are also going to maybe talk about the shear moment diagrams and what they represent. Alright, we also have a positive 6,000 pounds times 10 foot. And then we're going to have a negative R2, 15 foot. And doing the math, let's get the calculator out. Well, we have 12,000 foot-pounds plus 60,000 foot-pounds, so 3,000 times 4 plus 6,000 times 10. And then we're going to divide that by 15, and we're going to that gets 48. So R2, let's do that to kind of separate them a little bit. R2 equals 4,800 pounds, and it's positive, so we know that this is correct. So the first, I know I didn't say this at the beginning, the first thing you want to do when you want to do shear and moment diagrams is you want to solve for your unknowns, typically your reactions. And after you get your reactions, then you make another Fibonacci diagram, and you start on your shear, and then you do your moment. So anyways, and there's R1, R2 I mean, let's solve for R1 now. So now that we have one force in the y direction, R2, that is unknown, we will solve for that. And we're saying R1 is positive. Let's go left to right. R1 minus 3,000 pounds minus 6,000 pounds plus R2, which is 4,800 pounds. Alright, now we will go ahead and do negative 3,000, negative 6,000 minus 4,800 is 4,200. R1, so if you add these two, it's 9 minus that, and then put it on the opposite side. R1 equals 4,200 pounds. And then once again, if you need to show all your steps in your algebra here, no problem, just go ahead and do it. And those are our reactions. Now what we need to go in and do is, oh, that's not what I wanted to do, is we need to make these equal to what they are. R1 equals 4,200 pounds. That's not looking good. 4,200 pounds. And R2 equals 4,800 pounds. Alright, now we're ready to do our moment diagram. Let's go ahead and change colors again. V is a function of x. And this is generally coming straight down. And the first thing you want to do is figure out what your reaction is, and you go up. You always start at 0, you will end at 0. You go up. Your reaction, 4,200 pounds. So there we are, 4,200 pounds. Then we go, now we have nothing going on until we get to 4 foot. So it's still at 40,200 pounds. And I'm just going to put pounds down here because it gets in the way of this when you want to write small. So 4,200. Now we get to here. Now we have to go down 3,000. And that will give us 1,200 pounds. Then we go over 6 foot until we get to 6,000. That is supposed to be straight, but it didn't look too straight. Let's try it again. There, now we're at 6,000, and when this comes down like that, it's supposed to line up perfectly, but I'm not doing this on graph paper. So 1,200 minus 6,000 equals negative 4,800, which it should. That makes sense because we're going to be going up 4,800, so we want to be at negative 4,800. This is at 1,200. Go down. Negative 4,800. My handwriting is not the best. And then we go up. This is also negative 4,800. Alright, so there is your shear diagram. Now we're going to move on to moment. We'll move down a little bit. And remember, if you have distributed loads, you want to, in this free body diagram right here, you want to make sure that the when you make an equivalent load, you want to change it back to a distributed load. And we've shown that on other videos, and we'll more than likely do it again on future videos. Tell you what, I'm going to move this down just ever so slightly. If I can get this right. There we go. That looks a little bit better. I'm going to go ahead and break this up into areas. That's area 1. Make purple. Area 2. I'll tell you what, let's call it A1. A2. Let's do that so it's less confusing. And then let's go to pink-ish for A3. Alright. Now, since this is a positive, A1 is positive. At this point right here, it will equal the sum of the area in this box. So, what do we have? We have 4,200 times 4 foot, and that's what we get. So at this point right here, at 4 foot, you are going to be at 16.8, and that's in foot pounds. And that's going to be linear, because this is a distributed load pretty much. It just goes straight over. This is going to be linear, and I'll get in hopefully into that a little bit deeper. So this is, for instance, this is 300x, or actually it'd be 4,200x. So 4,200 times the distance, you're going 4,200 feet times x, which is how far? 4 foot, and you have 16,800. Now if you only want to know so this slope, how do we reckon? Let's call it S slope, equals 4,200x. And I'm going to get rid of that, but that slope is actually this number right here. Alright, moving on. Alright, so you could, actually I won't move on, I'll stop real quick. So you could take it at 2 foot. And at 2 foot would be right here. It would be the area right there under that curve, which it's not a curve, area under a square. It would be half that. So you could figure that out as well. It's 4,200, that'd be half. So what, 8,400 at 2 foot. You could do that anywhere. And that's kind of the benefit of doing a shear and moment diagram, because you will know the moments the entire beam. So if you want to change the reinforcing in a concrete beam, or you want to make a thicker flange, if you have let's say a plate girder bridge or a giant building instance, you could actually make the flanges larger, or you'll have to make the flanges larger for moment, and you'd have to make the web larger for shear. Anyways, we'll continue on. So we're still in the positive region. We're looking at A2, which is right here, and you have what, 1200 long or high times 6 foot equals 7200. So we're still adding. Since this is still positive, we want to do 7200 plus 16800. So A2, let's just write over here, A2 equals, oh shoot, that was 7200. And A1 equals 168. So together, at this point, right there, we get 24,000. No, Louis. That was Louis, my dog. Alright, and actually this is going to be a little bit less. And this slope, as you may have guessed, is 1200. So at this point it's 16,800. From that point on is 16,800 plus 1200 x, if you want to put it in this type of form. 24,000, I believe. There you go. Alright, now we need to do A3. And A3 equals, now we have 5 foot times negative 4,800. What is that? Pounds. And it should equal 2,400. And it does. And this is negative, remember. This is negative because it's below this 0 line right here. So it will go down. From this point you have negative 2,400. From this point you go down and you're back at 0. And that's exactly where you want to be. And remember this, from this point, this line is 24,000 minus 4,800x. So you could find the shear at any point along this x, which x is going that way. You could find the shear anywhere along that. And since we have a couple minutes, I'm going to try to throw in superposition. And I've mentioned this before, and I probably need to go ahead and get some diagrams and talk to AISC and see if I can steal some of their diagrams. But what you could do, you can look at this at a few different ways. And you can take, it's called the principle of superposition. I'm going to write this out because this is very important. If you get this, then you'll, I know Kung Fu type moment. It's very powerful. It's the principle, P-A-L-P-L-E, I'm going to go with P-L-E, of superposition. And this is great, meaning the shear and moment from here plus the shear and moment from there, if they were all alone, it actually equals the sum of the two. So you can actually break things apart and make easier the, so you can take, what was that? That was 3,000 pounds. And then 6,000 pounds. And you can add these, the two of these together, and it will come up with here. And I'm going to pause it real quick and go ahead and write it out and then describe. Alright, we have gone into the future. And as you can see, I've split the two loads up. And if you add the reactions, if you add the reaction at A, you get 4,200. If you add these two reactions, you get 42. And over here at B, you get 48. If you add these two shear diagrams, you will get this shear diagram. And the same for the moment. If you add these two moment diagrams, you will get this looking thing. So that gets very powerful when you have a lot of different things. It also does well with the equations in your steel book, where you can take distributive loads and whatnot. Makes it real easy. Very important.